colloquium. This one is by Zoom, although partly we have started sometimes by a hybrid mode. It's a great pleasure for us to welcome Professor Ashutosh Kotwal. This colloquium is being jointly organized by Ayuka and by Vigyan Bharati Pune, and we are thankful to them also for bringing Dr. Kotwal's dates to our notice and for them to be there in person. And probably most of you may not require much of an introduction to Professor Ashutosh Kotwal, but to say a few words, he is the Fritz London Distinguished Professor of Physics at Duke University. Did his PhD from Harvard, and I understand that he's joined Duke from 1999, and he has been there ever since then. Among various awards and achievements, he's also a fellow of the American Physical Society. He was part of the team which announced the discovery of the Higgs boson, and he's the lead person who is going to talk to us about the W boson and all the great things that maybe it foreshadows for some kind of revolution in particle physics. So it's a great pleasure again. Professor Kotwal, please take it away.
Thank you. Thank you for those kind words of introduction. On behalf of Fermilab and CDF collaboration, my colleagues who built the experiment and who worked with me all these years, I'm happy to present to you this latest measurement, and I should say it's in the series of measurements. I have been doing this for 27 years. The last three I published about 5 times, and the last 3 were from this particular collaboration and this particular experiment, which we call the Collider Detector at Fermilab, or CDF from short. So in this photograph, you see a particular zoomed version of the experiment. This is the drift chamber. Some of you know this inner region is the Silicon Detector, silicon tracking, which is not actually used in this measurement. But this outer detector, which is about 1.3 meters in radius, that wire tracking chamber is the heart of the analysis, as you will see. So I stole this title from the journal Science. So we published on April 8th. And as is the tradition of that journal, in addition to some scientific paper from some authors, they will often go and ask some other completely disconnected set of impartial people who have no relationship to that particular paper, and ask them to write some kind of synopsis or some kind of review article for the general audience, because the paper is often very technical, but the audience for the science journal is broad, it's all sciences. So those authors of the synopsis article, which is about 1 page, they titled their synopsis an upset to the standard model, as was hinted earlier. So I stole the title not from our paper, but their synopsis. So the talk itself will be sort of in roughly 2 halves. The first half will be motivational. What is at the heart of the standard model of particle physics? What are the axioms, very briefly? And what are the issues? So like any other theory, some of it is very axiomatic and very rigorous, and also on very sound, very strong experimental footing, like special relativity, like quantum mechanics, like group theory. But there are other aspects which are more phenomenological, sometimes parametric. An example of this is the Higgs part of the model, which is very phenomenological at this point. It has some good connections to some theoretical axioms, but a lot of it is just ad hoc. What happens if this were to be there, and then you proceed. So I'll give a little bit of introduction to that, and the second half of the colloquium will be getting into more technical nitty-gritty on how the measurement is actually done. And I might sort of go through the slides rather quickly at that point, and please feel free to ask me any details if I go too quickly. So on that note, let's start. What happened some time ago was this idea that a theory can be built on a set of symmetric principles, certain invariances, shall we say. that the equations written down are invariant under certain transformations or invariant under certain symmetries. Sort of like general relativity is a theory that obeys transformations of the metric, and that leads to a certain set of equations which we call general relativity. So this was an idea that was used to build the standard model of particle physics for quite some time. But then the things that would not fit, that would violate those principles, they were slowly attributed to the following logic: that you do not abandon the symmetry principles. What you say is that the ground state or the vacuum of the theory, which is the lowest energy state of that quantum system, the symmetry is not broken by the axioms, but it is broken by the ground state. So this went under the idea of spontaneously broken symmetry, which is just that the state formed by that Lagrangian or that Hamiltonian is the one that violates certain symmetries, even though the Hamiltonian itself, let's put it that way, does not violate those symmetries. And that's how it all starts to come together. So this was the idea here in 2008, Nobel Prize awarded for manifesting this idea. And then in 2013, the Nobel Prize was given for the Higgs boson discovery to the theorists, some of the theorists who wrote down some of those mathematics. But the idea again was you are seeing the vacuum, the actual vacuum, as a non-trivial ground state that has non-trivial quantum numbers because it is a condensed state or some kind of condensed matter state of this new Higgs field. So on that front, the question started popping up. We're never done, as was stated. Science keeps asking new questions when you answer the old. So the weak interaction mediated by the weak nuclear force, which we now has a quantum mediator, the W boson and the Z boson. So that's what the W boson is. It's the mediator of the quantum version of the weak nuclear force. The Higgs is a ground state of that system. So the vacuum is a non-trivial ground state with respect to this particular interaction. So how does that all work out? We don't completely know. What are the mysteries associated with the Higgs boson? Why is its potential what it is, and so on is not known. You all know dark matter is even bigger mystery. Another completely unsolved question is why is there more matter than antimatter in the universe? According to the standard model, the equations, the reactions of matter and antimatter are almost symmetric, not perfectly symmetric, but almost symmetric. And the conditions after the Big Bang, for example, were such that given the properties of the Higgs boson and so that we know, the symmetry of the matter and antimatter production and annihilation should be such that we basically should not have the matter excess that we observe today. So by many, many orders of magnitude, there should be much less matter. It should have annihilated away to a much larger extent. And yet here we are. So that is beyond standard model, not answered. And dark matter, dark energy is even beyond that. To my knowledge, there isn't even any way of doing quantum mechanics with dark energy or anything at all yet. So this is completely outside standard model. So to quickly recap particle physics, matter is now explained as fermionic. So matter and antimatter, whenever there is charged matter, then there is an antimatter with the charge transforming the other way. So we now have 12 fundamental fermions constituting all matter. And these are called the famous quark names, up, down, strange charm, top and bottom. And these are the particles down here that do not experience the strong interaction, the one that binds protons and neutrons together, for example. That interaction is also experienced by the quarks, but not the ones down here. So these are called the leptons, which are the electron, neon, and tau taus and the corresponding neutrinos. So many people already say that there is beyond standard model physics embedded in the fact that we are not offering any explanation whatsoever for why these masses are so different. So the theory of mass is it is dynamically generated by the interaction of all the quarks, in fact, all the particles, with the Higgs, with this ground state. So that's fine. But on the other hand, therefore, that interaction coefficient should be extremely different if you look at this small number versus this very large number. This is 175 billion electron volts. This is, as far as we know, much, much less than 1 electron volt. So now you just shifted the problem from why the masses are so different to why the interaction strength with the Higgs boson is so different of all these particles. So completely unanswered. All right. With that, we have a very strong theory of forces. So it is all essentially like GR. You are living in some internal space in this case, and that internal space can transform differently at different space-time points. And therefore, this curvature, constantly changing curvature of this internal space is how you manifest forces. So this is exactly like if you try to do Newton's laws on the surface of the Earth, which is a rotating non-inertial coordinate system, you generate Coriolis force as a sort of fictitious force. And so that explains why, in the frame of reference of the rotating Earth, why the Coriolis force will make the hurricanes look like they're going a particular way. So all of this is embedded in an extremely elegant looking equation. This is the famous covariant derivative. It's also there in general relativity. And this is in some sense the gauge invariant curvature. So this term tells you electromagnetism, and this covariant derivative acting on the fermionic fields tells you how the electromagnetic field interacts with the electron and the muon and the quarks and so on. So very elegant physics here. Then when this was applied to nuclear decay, things started getting not so obvious. Or these ideas of coming from electromagnetism weren't working exactly right. So here you see a nucleus emitting a beta particle. Eventually understood it's the neutron decaying to a proton with beta emission and a neutrino. That at the quark level now becomes a neutron contains these three quarks. One of those quarks emits the quantum of the weak interaction, which is the W boson, the topic of this colloquium. And that W boson is decaying to an electron and neutrino. So this was the fundamental picture describing weak nuclear decay. So the W boson is really, the math is so identical to the Coriolis force, it's effectively a duplicate, because the symmetry associated with the weak interaction is taken to be the symmetry associated with a sphere. And so the fermions are sitting at the two poles of the sphere, you could imagine that. And the transformations up and down the sphere are the W plus and the W minus boson in the quantized version. And the third type of transformation could be along the equator. And so that's the Z boson. So the three quantum mediators of the force are the ones that make the transformations up and down and around the equator. So three types of transformations, three force mediating particles of the bosons. So this symmetry has a problem because, like every other symmetry, the particles making the transformations must be massless. So the W bosons and Z bosons had to be massless, but they're not. The whole reason the weak interaction is so weak is because the bosons are extremely massive. So at low energies, you do not have the energy to produce real bosons. So the matrix element, the quantum matrix element is suppressed. So how do you solve this? They didn't want to abandon the symmetry. So another radical proposition, you just invent a vacuum state which violates the symmetry. So this is the idea of spontaneously broken symmetry. So all this is good mathematics and works out right. But the phenomenological or parametric part is, how do you induce such a ground state? And there you just invoke a potential of a particular shape. And you say the Higgs field, instead of sitting at zero, which is how you would like to think of the vacuum, there is nothing there, everything is zero. Instead, that Higgs field rolls down from a high potential energy to a low potential energy here, right there. And the way to do that is to create this famous sort of Mexican hat potential, whose minimum is down here and not there. So where does this potential come from? I mean, all the other forces we discussed, there is no type of potential. It is a symmetry transformation which is giving us the feeling of a force. Here, there is no such thing. So you have to literally put in the classical, undergrad level potential basically by hand. And there is no real explanation for the formation of this potential or what is the dynamics of this potential and nothing like this. So it's much more parametric in the Higgs sector, shall I say, as compared to the other forces, which are thoroughly axiomatic and symmetry based and transformation logic based and so on. Fermions are the same thing. The matter particles are very well understood. The gauge forces are very well understood, but the Higgs is actually very poorly understood. So in comparison to the gauge sector Lagrangian written up here, which is with a couple of numbers, it's all nice and mathematical and axiomatic. If you look at the Higgs sector Lagrangian, it's got all kinds of parametric things. Potential has a square term and a quartic term. Who knows what else could be there? There is the famous dark energy term. All the different masses are captured in all these different couplings between the fermions and the Higgs field. So why all these different values of this number, Hij, ranging over many orders of magnitude? very little fundamental science here. I mean, the symmetries are very well respected, but the exact form of this is just so written down and it sort of works. So we write it down. For example, why does the Higgs potential have to be purely quadratic? It does the job. It's the simplest thing that can do the job, but it could have, sixth order terms and eighth order terms and have all kinds of interesting shapes. After all, if it's a parametric potential, why limit it to this? So the reason to limit it to this was some theoretical instinct, basically, but no rigorous reason why it has to be cut off here and couldn't go on to some larger polynomial. So this is now a big area of research, try to understand what the Higgs potential really is. And it gets more complicated. So as you know, in quantum mechanics, you have to allow for vacuum fluctuations. So there are deep reasons why vacuum fluctuations do not induce masses for the gauge bosons. So the gauge symmetry is respected. But when you try to do the same thing for the Higgs, you get these vacuum fluctuations that have to be there because we know the couplings, we know these particles exist. But these quantum corrections are very large and very difficult to control. So if you let them run amok, which is sort of what quantum theory would do for you automatically, the Higgs mass itself would become extremely large, and the observed mass is so small that this is another thing called the hierarchy problem. What is keeping the physical mass so small when quantum correction should make it very large? So here's a sort of caricature of it. If you saw the Empire State Building or something with the tip at the top, if you saw it standing upright, you would say, yeah, that's a stable configuration. The base is broad and the tip is narrow. That's stable. If you tilt it a little bit this way or that way, obviously from mechanics, it will come back and reduce its energy. But this configuration is very unstable. It has the slightest tilt and it will just fall over. And yet, this is sort of how the Higgs boson mass is appearing to be tuned. It doesn't become large, even though it ought to become very large. So how does it remain small? It's widely considered as a conceptual weakness of the Higgs theory under the rules of quantum mechanics. Even worse, the potential we said was at least has a phi to the fourth term. So this term also receives quantum corrections from quantum vacuum fluctuations. And for a particular set of parameters, it does something horrible, which is that a potential which has a minimum and then goes up. In fact, under quantum corrections, that potential going up can turn upside down and come down again. So as you all know, potential that comes downwards means the minimum value is now completely undefined. If you happen to get out of some local minimum, you would jump out there and keep rolling down forever. But this is playing with our actual vacuum in which we are living, right? The universe. So the unstable vacuum or the unstable universe is a very bizarre thing. How is it exactly getting balanced and why would we happen to be remaining stable? So you do the math and you find that those quantum corrections depend on the particles undergoing the fluctuations. So the top quark mass is important, Higgs mass is important. And this region would have been completely unstable vacuum. This region would have been a stable vacuum. And as it happens, the Higgs mass and the top quark mass are living in this tiny sliver of metastability, which means the potential really goes up and then comes down again. So eventually it will sort of do some quantum tunneling into the unstable vacuum, and that's the end of everything as we know. But we happen to have a long enough lifetime that the quantum tunneling probability is small, and so we are metastable. So all very, just so lucky and all this, which is not a very satisfactory situation for, you might say, a fundamental theory. So here is the funny behavior of the Higgs, which perhaps we are getting an actual particle physics hint from, because the fixes to these weird behaviors in the theory are motivating standard model extensions or additional physics, which would stabilize all this. And we might be seeing the effect of those additional particles or additional forces or additional mechanics in this mass of the W boson, which is presumably sampling all that new dynamics. Okay. So another motivation is dark matter. So we know it exists for a very long time. We know it through its gravitational interaction. But it could be some non-particulate thing. It could be some field, classical field permeating things and so forth. But the other hypothesis, which seems to work for everything else so far, is that eventually you drill down and everything is made up of particles, which are now in the standard model. but there is no standard model particle that explains dark matter. It doesn't, none of them have the right properties for dark matter. So if you extended some symmetry and included some more particles for muonic or bosonic, then those could constitute the dark matter. So many beyond standard model theories have some dark matter candidate particle in them. Last one is this famous matter antimatter symmetry. So three conditions, famous scientist and peace dissident, peace advocate Sakharov, he postulated these three criteria, violations of certain symmetries and departures from thermal equilibrium. And this latter one is important because whatever asymmetry is created, it might wash out. But if the universe were to freeze out very quickly, if the Higgs state were to form, ground state were to form very, very quickly, technically it means with a first order phase transition and not some other slower transition. So as the standard model stands, that phase transition is not first order. So here is the Higgs field, and here's the potential associated with it as a function of temperature. So you need the temperature dependent potential shape to become like this so that you get a rapid first order transition, and that would create the necessary conditions for locking in the matter excess. But currently we have the right hand side picture. The standard model as calculated gives the transition in the right hand side way of looking at it, which is called a smooth crossover transition. So here, the Higgs freeze out in some sense happens so slowly that the expectation is that all matter, even if it's created because of some asymmetry somewhere, would wash out. So you wouldn't lock in the matter excess. So you have to do a rapid freeze, so to speak, which is the first order phase transition we do. The problem is the standard model does not have a first order phase transition for the Higgs condensation process. So we need something else. Okay. So with this, let's come back to the W boson logics, and I'll show you, what type of ideas people are presenting. But now let's get into the technical nitty-gritty of how the measurement is done. So firstly, I mentioned the parameters of the standard model. You have two gauge groups, and those gauge groups are the symmetry transformations because of which we experience the electromagnetic force, so to speak, and the weak interaction. So those two groups have two coupling strengths, and then there is a mass scale induced by this ground state of the Higgs. So in these three parameters, without going into too much detail, we can come back to this, are very precisely experimental parameters. And within the standard model, you can infer from these one mass scale and two couplings. So now that part of the sector is fixed. So with those, you can already calculate an MW. So you have a prediction. This prediction is not complete because you have to include the quantum corrections. So in some sense, that was the classical prediction. And now you have to use the quantum fluctuations to add additional self-energy corrections. So here is a W boson experiencing a quantum loop with a top quark. Here it is experiencing another vacuum fluctuation with the Higgs boson participating. And so now that these couplings are known and all these properties are known, in some sense, the standard model is now sort of has a bullseye on it because the W boson mass, including all these known quantum corrections, is extremely well pinned down. So now you're highly motivated to measure it because if you see a difference, then in the continuation of this logic, it means perhaps that you are seeing the quantum fluctuations of unknown particles, which you may not have the energy to observe, but they do participate in the fluctuations, just like the Higgs participates and the top quark participates. So that may be what we are seeing. So on the experimental front, this is the precision we are chasing. So this is the precision on the theoretical expectation. So you see a very well pinned down number that you can see whether your measurement agrees with it or does not agree with it. So this is it's a perturbative calculation. So, the perturbation series is truncated at some point, and it's estimated what contributions you might be missing because of the truncation. So this is the 4 MeV out of all this large number, 80,000, is the truncation error, so to speak. And the calculations of those quantum effects include inputs like what is the mass of the Higgs boson, more importantly, what is the mass of the top quark, what is the mass of the Z boson, the unknown parameters of the theory that have to be determined by experiment. So experimental errors also contribute to this prediction. But on the whole, if you put these together, you see that the expected value is now calculable to a 10 to the minus 4 level precision. So you want to now go and measure the W boson mass at roughly the 10 to the minus 4% precision. So in the high energy physics world, this is probably the most precise measurement of something fundamental that we have, excluding electromagnetism. Electromagnetism has some way more precise measurements, but other than the electromagnetic sector, this is probably the most precise. Okay, so this is a survey of new ideas. I think if time allows, we can come back to what we might be seeing, but this is just there to so for completeness. I'll mention one, which is a dark sector idea. So it's interesting that you may have particles which do not experience any standard model force at all. So not the weak interaction, not the strong interaction, not the electromagnetic. And since they're all explained by symmetry principles, it's sort of easy to incorporate these because you just say, well, here's another particle that does not participate in any of those symmetry transformations. So since the others were just invoked and nature seems to follow them, you can certainly invoke particles that do not transform under any of those transformations. So in simple language, they have no standard model charges. So they won't be interacting at all, except they will interact with the Higgs boson for quantum reasons. They may have the same quantum numbers. So for that reason, because the Higgs boson interacts with everything else, and this new particle may interact with the Higgs boson, you eventually start to see the effect of the dark sector, so to speak, on the visible particles. So you sort of start to wonder maybe there's a connection with dark matter as well, because if the visible particles and the dark matter particles did have some kind of interaction sometime in the past, you start to understand how you might have created the dark matter in the first place. Okay? So even such a simple change to the standard model induces effects that are visible, small but visible, such as a correction to the mass of the W boson away from the standard model value, because you just changed your calculation. So this is the sort of thing that motivates why we are chasing this precision for so long. So this I picked this example because just the addition of this one additional, even simpler Higgs than the one we have, the second Higgs, is enough to actually make the transition, the phase transition of this ground state, of the Higgs ground state, from the transition in the standard model, which is not adequate, to the first order transition, which is what we need. So this simple change will satisfy one of the Sakharov conditions for creating the express matter in the universe. So it feels quite attractive to see, does that particle also create a change in MW? And the answer is yes, it affects the MW by quite a bit actually. So it's target to measure. Another famous theory, supersymmetry theory, many nice features about it in a theoretical sense. At the same time, it has therefore been pursued very heavily at the Tevatron and later at the Large Hadron Collider now, even in the future, because it might have escaped detection somehow. So production of supersymmetric particles might have escaped us for this reason or that reason. Perhaps they're too heavy to be produced here to somebody. But at the same time, they participate in the quantum corrections. They have the charges associated with the W, so they will participate in the vacuum fluctuations. And that will induce a correction to M. So this is where we were in 98. You see MW versus the top quark mass, a region where supersymmetric particles contribute with this additional contribution. A region down here where only the standard models are considered, standard model particles are considered in those quantum effects. So if the mass of the top quark and the W boson showed up in the red band, it would be consistent with the standard model. If it showed up somewhere here, it would be requiring some additional contributions, such as supersymmetry, among others. So this is the situation now. In 2012, the Higgs boson mass Higgs got discovered and the mass got fixed. So this standard model region then collapsed to this purple line. So the quantum corrections from M top and the very well-known Higgs value would give you a line like this. And if MW, the vertical axis, were on the line, the standard model would still be respected or agreed. If it was falling not on the line, you would have to invoke some additional principle. So, and this is the reason we are here. Our measurement is now significantly different from this line. Okay, so moving on to measurement issues. So it is essentially a quark-antiquark annihilation process, producing the W, and then that decays to an electron or a muon and other things too. But we are going to focus on the electron or the muon because that is something you can measure precisely. And in addition, you have a lot of initial state strong interaction physics. The quarks are radiating other particles which mediate the strong force called the gluons. And so the W boson isn't really produced in isolation. It has a lot of other particles coming along with it. So the precision at which you measure the momentum of the lepton, the electron or the muon, is the vital thing. It also matters to some extent how well you measure this. So let's go quickly through those things. I'll mention very quickly, this is the drift chamber, which we use for calibrating very precisely the electron and the muon. This is the calorimeter, another device that measures the energy of the electron. And these devices around here measure the energies for all the other particles produced in the event. Here's a photograph of the same thing. It's about 30 to 40 feet tall and roughly about the same in the width. So it's like a huge 3 or 4 story house. And here's a computer generated image of what a collision would look like. The detector is cylindrical, so the beams are colliding in the middle, going into the page and out of the page. And so then the particles are spraying out in all directions like this. So what you actually detect are the little black dots. Those are sensors which light up or which record an electric charge when a charge particle comes through close to it. So what you see is a huge bunch of little black dots, but you know that the black dots are connected by helical trajectories because the charged particles in the magnetic field are bending. So they are creating helical trajectories. So we have to do the inverse, which is connect the dots and create the charged particle trajectories or infer the charged particle trajectories from connecting the dots. So it's a big program that does it. And one of these is the electron. It's also recorded in another detector called the calorimeter. So you see the energy of the charged particle here. When it matches the energy of this other kind of detector here, then you know that it's an electron because it's supposed to have roughly the same energy measured 2 different ways. Okay. Big problem with W boson analysis is the other particle that the boson decays into is a neutrino. You cannot detect it. It's essentially invisible to us. So it has to be inferred. And all the things that go into making that inference are the reasons why this measurement becomes difficult. Okay. Let me not dwell on this slide. It just tells us how, from all the particles produced, how you select out the W bosons. We are using the data from the entire roughly 10-year run. You will notice the run stopped about 10 years ago. So we've been doing this analysis for 10 years. And here's the number of events we have in the W bosons decaying to electrons, muons, and also Z bosons decaying to electrons and muons. Okay. Some technical detail here. Let me flip over and come back to it if time allows. So we'll follow this strategy. We'll try to make calibrations and all the other things needed to make the measurement as confident as possible, as precise as possible, by doing the same thing many different ways. If you get the same answer, then you're more and more confident. And of course, because you're getting multiple measurements of the same thing, you can also combine all those and increase your precision. So robustness leads to precision. One thing we have been doing for 20 years, which other measurements of MW haven't done, is in a sense to demonstrate that you can trust the MW measurement that we have, is that we will also measure the Z boson mass at the same time. The Z boson mass has been measured independently much before us and very precisely. So by showing that we can get the same value, in a way we don't know what value we'll get. We will do all the calibrations without knowing this value. Then one day we will look at what value we have. This is called blinding in our field. By doing MW measurement blinded in the same way as MZ, if we get the right value for MZ, that's one more piece of evidence that we are confident about MW, which is what we're after. Okay, let's move on. I will show you a few technical details on how the drift chamber works. So filled in here are a whole bunch of wires, 30,000 wires, and they're sitting at high voltage in a gas. So when a charged particle comes through, it ionizes the gas. The sense wires are put at a high voltage. So the ionization charge then drifts towards the high voltage wire. And by timing how long it takes for the drift to occur and knowing very precisely where the wire is, you can then infer where the particle must have gone through. So this is how you record the positions of the wires of the particle as it traverses through this large volume of wires and gas. So now you have to know exactly where the wires are. So this is a special technique. We wrote a special paper on, myself and my student in postdoc. The cosmic rays, which are muons coming from the sky, they are going through the drift chamber. And so we record their positions on both the top side and the bottom side. As you see, these little dots are the recorded positions. And because they must lie on a single trajectory, if any of the wires are displaced or you got the position wrong, then it shows up as a deviation from that smooth trajectory. So this is called alignment. It's like a surveyor lining things up. So this technique is incredibly powerful, as you will see on the next slide. Let's just focus on the bottom plot. This is recording on the y-axis how well those recorded positions line up after we perform this this procedure. So initially they don't line up. You see the scatter is some wire is in the wrong place here, it's in the wrong place there. But by applying this logic, you find that after applying a correction in software, they line up just beautifully. So this is a 1 micron level alignment. Human hair is 100 microns thick. So this is 1/100th of the thickness of a human hair. Is the precision with which you know the positions of all these wires. A little more technical detail, it's a check that the procedure is working correctly. So this logic says the same particle is going from the top and then coming out at the bottom. So if you make the measurements of this particle in one half of the detector and the other half of the detector at the same time, it's clearly the same particle. So if you compare the properties of that particle that you measured from the two sides, if everything was properly done, then you should get the same answer, roughly the same answer from the two sides. In other words, if you compare the two, you should get essentially zero. But there is some natural accuracy with which you measure it. So you cannot get exactly zero. But you see that the distribution of this comparison is very nicely centered on zero. And this is just your experimental or detector resolution. So there's some fluctuation, but it's a very nice symmetric Gaussian fluctuation. And these are the parameters you're measuring for the particle. This is another parameter you're measuring for the particle. So all the measurements you're making from this sensor device are consistently matching each other from two different parts of the sensor. So in a way, this is convincing us that this sensor is nicely understood. Okay? Skip some detail. There is more such things we can do. This time, instead of using cosmic rays, we can use the electrons and the positrons from within the data. So the W bosons are half of them are positive, half of them are negative. So half of them are decaying to positrons, P plus, the other are decaying to electrons. There is a particular metric you can make that checks if that sensor we're just talking about is measuring correctly. And one very nice idea is you can compare positrons with electrons, this particular quantity. It's supposed to be identical if the tracking device is working well. So all the things I showed you before were actually true, then this difference should be zero. And so we make a plot and we see how close to zero they are. And that's telling us how well the device is actually working. So this is a function of polar angle, and they're very nicely near zero. So I will quickly flash forward and say, now what will we do? Once you have the tracking device, I'll come back to this video, you can start calibrating the device, which means, in other words, you have to know the magnetic field. So it's textbook physics. You're saying if you know the trajectory, you can therefore decide that it's a circle. A circle in a magnetic field, if you know the radius of the circle, you know the magnetic field strength, you measure the momentum. So the momentum is just a simple function, textbook physics of magnetic field momentum. Basically, a charged particle bends in a magnetic field, and the lower the momentum, the more it bends. So to measure the momentum, you have to measure the radius of curvature, and you have to know your magnetic field. So you can never say that I know my magnetic field just like that. So the idea is you take some other particles whose mass you know very well, This is a famous particle called J psi, um, and its mass is known very well. We will measure its mass in our own detector, and we expect some difference because there is some magnetic field correction or something you have to make. And so that allows us to calibrate our detector so that we can get the right value of the J psi, which is already known. So this is our procedure. We are calibrating on the J psi. Before I move on, I'll quickly flash a few slides on theoretical logics. So we have to understand how W bosons are produced. We have to understand how they decay. We also know that charged particles radiate electromagnetic radiation. So there is a lot of computer code involved from other people who make all these calculations, and we incorporate those calculations into our analysis. Let me skip some of these details and show you maybe one plot that says, all right, so these W bosons are produced accompanied by strong interaction physics, so accompanied by other particles that undergo strong interactions. So because of this, the boson is not produced at rest. It has some momentum in the transverse direction, perpendicular to the beam. So what is that distribution of that momentum? So that's what we call momentum transverse, or PT. So the same logic applies to Z bosons. There you can measure the momentum by measuring the two particles into which the Z boson decays. So this measurement, which is in the blue dots, helps us tune up the calculation. So the calculation has a lot of physics telling us what the spectrum should be, but there are always small parameters that can change a little bit what the calculation is. So we can tune those parameters until we get the right answer for the momentum spectrum of the Z boson. Another study like this will tell us how the W boson spectrum will also be calculated and also be anchored on the data. In other words, we are not trying to rely on these calculations as much as possible. We are trying to use our own data to pin down exactly what those calculations will be like. So more studies here. So I'll flash a few plots like this, but you will notice in general the theme is that there are many things you have to understand about how the W bosons are produced and what energy the particles will have that the W boson decays into. And from that energy, you have to apply some logic to figure out what the mass of the W boson must have been. And every one of those inferences requires you to know some additional information here, some additional information there. To the extent possible, our logic is we will extract all that information from our own data, as much as possible guided by well understood physics principles. So in one sense, we are checking the standard model, but we are checking one particular aspect of the standard model, which is the quantum corrections experienced by the W boson, potentially because of supersymmetric particles or dark matter particles or something. But at the same time, we are not abandoning all the other concepts in the standard model, such as the theory of the strong force or the theory of the electromagnetic force, or fundamentally what a fermion is, what a boson is, and so many concepts of quantum mechanics and so on. So everywhere that we can reliably trust known principles which have been checked against the data, and when those principles are validated as much as possible by our own data, then we keep using those aspects of the model because that gives us more and more information that we can put in all those inferences. So broadly speaking, it means the analysis technique does rely on other pieces of information, and you're getting all that other information from other aspects of the standard model which are not in question. I mean, and to a certain extent, if they are in question, then we are having our own data to pin down potential variations in those aspects. So it's a big sort of program of analysis that takes everything from here, there, known things from past experiments which are not in question, things that we observe in our own experiment, which we can use to pin down all those other ingredients, so that finally you're able to say, I've got all those inferences understood. Now I'm able to say what the mass of the W boson is. For example, let me just go to the next slide. Here is an image of the silicon detector. So this is inside, on the inner side of our entire apparatus. So all the particles we are talking about are produced in the middle, and then they fly outwards. And as they go through all these sensors, they are of course experiencing various kinds of material interactions. Charged particles always interact with material. And that means that they will lose energy by one of many processes. They're all electromagnetic processes mostly. But there's a lot of literature on those electromagnetic processes that has been measured many other places. So we've documented all of those things, and we said, therefore, we know exactly how an electron would behave when it passes through a material of lead or a layer of silicon or a thickness of aluminum, whatever. Separately, we have measured all the various types of material that are present in the fabrication of our sensors. So that put together allows us to calculate all the different detector effects. So understanding our detector at a lot of detail is mostly the thrust of the analysis here, to understand many things that go into the analysis. Let me skip some details here. Now we come where we were a little bit earlier. Here is a measured distribution of what we call the invariant mass. It's the 4 momentum of one muon combined with the 4 momentum of the other muon. So now you have the 4 momentum of the decaying particle, from which you of course get the invariant mass. So that is a distribution of the invariant mass as recorded by the detector. It should be a very narrow peak, but of course you have sensor resolution. So the sensor resolution makes it somewhat of a slightly broader peak. It's still quite narrow. The red line is our simulation matching what is happening in the detector. And from that, we are able to extract what the mass of the JSI particle must be. When we compare that to the known mass, we say, oh, that means we have to calibrate our magnetic field or something, for example. We don't know exactly why we need the calibration, but we do need a small calibration. You see what that calibration constant is. It's about 1.4 fards per thousand. 1.4 parts per thousand. It's as if our magnetic field is, as recorded, is slightly wrong by 1.4 parts per thousand, or some other aspect of the detector is slightly off. However, apart from that one calibration, the fact that you can change the momentum of the particles coming out of the JSI and yet keep measuring the same mass is indicated by the fact that all the separate measurements here, to a certain extent, of course, line up along a horizontal line. And you can imagine, I won't go into too much detail here, but some of the points are sort of not so far from the line, not so close to the line. Here are a few points not exactly on the line. So people have asked us some good questions about, I'm here making the case that we need one calibration which is independent of momentum, but not all your points are confirming that. Many points are confirming it, but few points here are a bit odd looking, and maybe one point here is a bit odd looking. So we looked at that very carefully. So just making a disclosure of the scrutiny that at least we have put our data through. So now we can come to another particle. This is called the epsilon. In particle physics language, it's a bound state of bottom quarks, and the JSI is a bound state of charm quarks. So the charm quark is a famous 1974, what is called the November Revolution from 1974, when that particle's discovery led to the understanding of particle physics in a very big way. Sometime later, the bottom quark was discovered, so that also has a bound state, bottom quark and anti-bottom quark, which is called the epsilon. So same logic there. You can reconstruct its invariant mass, and you get a nice peak. So now we can ask the question, skip some detail. Having calibrated on one particle, are we measuring the mass of the next particle correctly? That's a proof. And the answer is indeed is yes. And I'll just flash, let's not look through all the numbers. But if you notice, we are studying the various calibration related issues at the level of sometimes 1 part per million, sometimes maybe 10 parts per million. And the known value of the second particle, the epsilon, is actually already worse than the calibrations that we are able to infer internally. In other words, some of the calibrations that were done by other people have already been surpassed by the analysis we are doing here. So calibrating on the J psi, this mass does come out correctly. I'm not showing you the exact value. I'm telling you in a plot that's about to come up that it's coming out to be the right answer. And finally, one more validation. The Z boson, which is another mediator of the weak force, just like the W, its mass was measured very well in the past. That experiment could also measure the W, but not as precisely as we can. We can also measure the Z boson mass, but not as precisely as those experiments. So, it's complementary colliders and complementary type of particle physics. But here we can say, look, our measurement of the Z boson mass is this number. Within the precision that we have, it's actually very consistent with the previously known number. This one is even more accurate than this one. So we can't claim any, there's some claim on a more improved measurement or anything. But it is a demonstration that we can trust our analysis at a precision level, something like this. And finally, what we quote as a precision is a little more than this. It's about 10 as opposed to 6.4. So it's an important part of our demonstration. And I would say that we have demonstrated this 3 times in 2007 and 2012, and now this, always with higher precision. There are, of course, other experiments also measuring the W boson mass, clearly an important quantity. But they have not made this particular demonstration of validation, shall we say, of the technique that if you want to measure X, you should show that you can also measure Y with roughly the same precision. And Y is known, so that's a proof that you're getting, hopefully, the right answer. So here is, in a way, a proof that this red point, which comes from the epsilon, the blue points come from the J size, and the green point comes from the Z boson, that within the level of precision we are showing here, you can see this bar, vertical bar here and a green bar there. That's the level of precision that is attributed to each one of them. That within those precisions, they all intersect this black line, and they are all combined together finally to get this one point. And this point is the precision with which we say we have understood the momentum calibration of our experiment. Okay. Similar techniques are applied for electron measurement. This was mostly focusing on muon. I'm going to skip this slide in detail, just show you that there is a separate paper written by me and my postdoc on applying similar first principles logic to how well you can understand the energy measurement of the electron. So far you are measuring the energy moment measurement of the muons. Now we'll apply similar logic to electrons as well. So it's another detector technology, so it has to be studied in completely different mechanisms involved. So we studied those mechanisms and wrote a paper on that one, published separately. So all of this knowledge can now be put to, for example, calibrate the second detector. For example, here is the energy measured in one detector called the calorimeter. Here is the energy moment measured in the tracking device, which I've been talking about, this big circular thing. Now, if those two energies or momenta are the same, then this ratio should be roughly 1 or close to 1. And you see, in fact, a nice peak close to 1. There's a reason it shifted slightly. It's technical detail. So you might wonder, what is this? What are all these events where the energies definitely don't match, 40, 50% different? And this is where electrons coming through the material, through the apparatus, every so often the electron will radiate electromagnetic radiation. That's what charged particles do. They always emit electromagnetic radiation. So when that electromagnetic radiation is large, then that energy is removed from this particular measurement. The photon, which is neutral, is not visible in the charged particle detector. So it's gone from the denominator. However, it's also measured in the numerator quantity. So this particular detector, the calorimeter, is able to measure electrons and photons. Therefore, it's present in the numerator quantity, but missing in the denominator. So the denominator is smaller. And so this gives a large value of this ratio. So we have to understand this part of the spectrum and this part of the spectrum. So our understanding is demonstrated by the calculated version of this, which is the red line, and the blue points are the actual data points. So the blue and the red have to match very, very well. So of course, we take the difference of the blue and the red and show that the difference is uniform, and essentially there is no difference. So the match is perfect within a particular variance, shall we say. So that the excellence of the matching, shall we say, is a way of showing that our um, calculated distribution or calculated spectrum of this quantity is describing exactly what the real apparatus is doing. In other words, we have a very high accuracy simulation of what is happening in the real apparatus. That's a very big part of the analysis technique here is simulation. You have to be able to show that you can understand your apparatus completely. Some more detail here, you see these points, calibration points, like I showed before. This time is plotted as a function of the energy of the electron. So if you calibrated the detector, then this factor, the calibration factor, ultimately should become 1, and it should be the same independent of energy. So these separate measurements at different energies within the variances, within these error bars, you see all line up nicely, consistent with 1. More of these calibrations. And finally, we come to showing that the Z boson mass also, when it decays to electrons. So previously, I showed you the proof that the measurement with the muon channel was working well, meaning consistent with the previously known quantity. And now we are showing that in the electron channel, it's also consistent with a somewhat worse accuracy, but you see the agreement is just fine if you allowed for this accuracy. Another demonstration that we have done 3 times now in these last 20 years. But the other experiments that are making the W mass measurements you will have seen have provided other validations, of course, but we think this one is important and none of the others have provided this one. So that's one of the reasons I would say we are confident. Okay. Little more detail here. In summary, what this is saying is I mentioned that the electrons radiate electromagnetic energy sometimes, and sometimes they don't. You saw one part of the spectrum and another part of the spectrum. So are we understanding the electrons in both regions separately, the radiative and the non-radiative? So this is a way of selecting. This first line here is both electrons are not radiative, and the last line here is both electrons are radiative, and one of each is the middle line. The question is, are we measuring a consistent value of the Z boson mass with the 2 different types of electrons, which is a difficult demonstration. And again, if you compare the known value and our value, they always agree within the precision we are quoting of our value. So whatever that precision is, we are getting good consistency. I'm going to skip some detail. Maybe let's skip a little detail. I like to leave time for questions. The last thing I will spend maybe, a few minutes and then we can conclude. When did we start? We started at 4 o'clock, right?
Yeah, we are like 4:58 now. Yes.
Good. Okay, so I think I can wrap up in 5 minutes. The last piece of the calibration is all this other activity in the event. It needs to be known, and all of that comes about because of this complication that for W bosons, the neutrino cannot be measured directly. Otherwise, we wouldn't have to care about this. But if you have completely missing momentum because of the neutrino, then the only one way to invert the mass, which is quite a good way, is also measure the rest of the event activity and then combine all the momenta that you know and try to get some more accurate measurement. So that is why the energy measured in all the other particles in the event, which I showed you, a very busy event, is sort of necessary. The basic idea there is in a Z boson event, the momentum carried away by the Z boson, which is being measured by the muons in this case, has to be balanced by the momentum carried away on this other side, because the initial state, the proton antiprotons are coming exactly along the axis. So they have no momentum in the perpendicular direction. In other words, what we call transverse momentum is initially zero. So therefore, the transverse momentum of the final state must also be zero, the simple momentum conservation. And that balance is allowing us to calibrate this side. Okay. So with this, I will just show you, what a balance will look like. You take one quantity, you add or subtract the other, and now you just project the vectors, vector sum on one axis or the other axis. And if things are balanced, you should get zero on average. So that's what this is saying. On zero, you're getting average. There are some reasons why it's not exactly zero, but the important thing is the simulation, which is the red line, should, within the uncertainties, match the data. And so sometimes it's close, sometimes a little far, but usual logic, you apply a statistical chi-square goodness of fit test, and that's how you calibrate. So these are just many distributions of that balanced quantity, and you will again and again see data versus simulation. And to a large extent, that's the heart of the analysis. You have to understand all the measurements and show that your calculation of all those aspects is consistent and explaining your detector and everything very well. So let's not worry about exactly what the distributions are, but they are just calibration distributions showing that the red line, which is the calculation, and the blue, which is the data, are matching. So let's just flash. And there are many more of these in the paper. For the people within the field, we have to demonstrate that all this is working well. And that's a standard technique in our field, is to show that your simulation and your data are agreeing well. And I would add that the level at which we are studying this validation of our understanding is much, much more. So I wrote this word new a few times, because compared to our 2012 analysis or 2007 analysis, we are checking many, many more things than we ever did in the past. And so we made that statement in the paper too. So don't even bother reading all this. I just left it for completeness in case somebody looks at the slides afterwards. But you just want to look at the consistency of the data and the simulation. Okay. We can come back to this blinding, but I think in the interest of time, I will just wrap up now. These are the distributions from which you extract the mass. And the basic idea is that the momentum, or a momentum-like quantity of the electrons or the muons that are coming from the decay, that momentum is roughly proportional to the mass of the W, which is decaying. So if the W was slightly heavier, all of this momenta would be slightly larger, which means this entire distribution would be shifted slightly to the right. And if the mass was slightly lower, then the distribution would be shifted slightly to the left. So the red line is a calculation for every hypothetical W boson mass. So you're only seeing one red line here, but actually there are 5,000 separate red lines which are computed, one for every potential W boson mass that nature might show. And then it's just statistics. You say which of those hypothetical curves is matching the data the best. So in statistics language, it's simple maximum likelihood fit. And that tells you what the maximum likelihood mass value you're measuring is. Then you do some simple checks and many complicated checks, which is it a good fit? So again, look at the distribution of data minus the simulation. And that should on average be zero. Of course, it will fluctuate like data fluctuate, but should on average be zero. So same fits are being done in many different ways. And on average, you can see zero. More fits, and on average, you can see zero. All of those different fits roughly give the same answer. So that's good because they're different quantities. Again, if you get the same answer different ways, you're more confident. Let's skip some details. This is number one figure in the paper, the source of all this upset business. So here is the line on which the W boson mass and the top quark mass should lie because of the vacuum fluctuations of the top mass and the Higgs boson contributing to MW. give this answer. So the purple line is the standard model answer. And if you are significantly different from the standard model, you're implying the existence of some additional quantum fluctuations, potentially supersymmetry particles or something else. Okay. So maybe I'll leave it at this. Is this my last slide? Yes. That something similar happened some time ago, way early when quantum mechanics of electromagnetism was being formed. So quantum field theory was being formed for electrodynamics. Uh, these kinds of vacuum fluctuations in the photon propagator this time were eventually worked out, and Willis Lamb made this very precise measurement of two different atomic electronic states of the hydrogen atom, and he saw a small 4 parts per million difference essentially. And eventually it was worked out that that small difference was because of the vacuum fluctuations in the photon propagator and also on the vertex here. So these are the virtual photons fluctuating in and out of the vacuum that made this tiny energy difference in those two states, which were expected to be some difference, and this was an additional difference. So this 4 parts per million was explained by this calculation, which eventually led to a real understanding of quantum electrodynamics as a real quantum theory. So I don't know. I just want to flash this 3 weeks into the our paper being published. So April 8 to 25. Already there was some 60 papers postulating all kinds of new ideas, or not so new ideas that might explain this. I think that number has gone up to 135 or so the last I looked. I can't keep up anymore. So now I'm looking at workshops where other theorists are summarizing the postulates being put forward by other people, and I'm just looking at the histogram of the different ideas put forward. So with that, let's stop here. Thank you for your attention. Here is the note at which, like you said, we are now sitting at, that people are thinking maybe this is the first strong indication of extensions to the standard model because of this 7 sigma discrepancy, which at the moment, nowhere in particle physics is there a 7 sigma discrepancy. There's not even a 5 sigma discrepancy anywhere else, ever since the Higgs boson was found. So maybe we are onto something. Let me leave it that way. All right, thank you.
Fantastic. Thanks a lot, Ashutosh, for this wonderful summary and very careful analysis which has gone on to do all this work. And I'm sure there must be questions. Already I can see one hand up. Please raise your Zoom hand and I will ask you to unmute and then ask your question. Yeah, Shantanu, please go ahead.
So I have actually 2 questions. Can you hear me?
Yes.
I'll just ask one now and maybe I'll ask later after others ask questions. So I guess, does the D0 result agree with the CDF result? And if not, do you have any speculate or reasons as to why it may not, why it doesn't agree? So I guess, can you show the D0 result also?
Yes, this one. So I'll tell you everything I know. First of all, the D0 result is done with an older version of a Parton distribution function. So this is what is the momentum coming from the quarks that are colliding. And that's always been a small but important effect. And people always worried how well we will know this, because in hadron colliders, you have to know the quark momentum for this measurement, unlike an electron collider where the electron has all the energy. So here the quarks do not have all the energy. The Parton distribution knowledge being used by the old D0 measurement, if I were to infer, knowing the correction that we had to make to the newer knowledge, this number will increase by 15. So the 376, in some sense, should be corrected to a more modern input and become about 390. Then you can ask 390 versus 433 with their uncertainty of 23. What's the difference? It's less than 2 sigma, slightly less than 2 sigma. So consistent within 2 sigma, you might say. Okay. The other thing which now it's fair, right? People ask us, we can all ask each other because ultimately we're all colleagues. They did this in two pieces of the data, and their own measurement from 2009 was actually much closer to this one, 2 hours. Then they did a second measurement from additional data which they published in 2012, and that moved down. So there was much more consistency a few years ago. They were over here somewhere, and then they moved down. So I should also say one third thing. This measurement from D0 is using about half of the total data. Our measurement here is from the full data at the Tevatron. So I've been extremely hopeful in a way that they will also analyze the second half. Everybody likes confirmation. So I was hoping to see what answer they come out, whatever it is, moves here, moves there, whatever. But I think it's been made publicly known by D0 colleagues that they are not going to analyze the second half of their data. So something about the detector has degraded, and they are no longer able to extract good enough precision measurement from it. So they've sort of abandoned it. I don't know how official that is, but they're saying it in conferences. So unfortunately, we will not get an additional measurement from D0 on the second half of the data. So the first half produces a precision of 23, and we are less than 2 sigma, but more than 1 sigma different. You can sort of imagine, getting that additional data analyzed would be quite nice. Who knows what will happen, but your question is prompting that in a way. But we may not get it. I sort of feel unfortunate. That's unfortunate. I'm told some kind of radiation damage started happening, and then it got worse and worse, or something like this, and eventually the second half of the data are hopeless. I think that's what they say. So
thank you. Maybe we'll go to Surut first and then come back to Shantanu later.
Okay.
Yeah, thanks for this talk. And it's always interesting to see precision measurements and then later on questions about whether these can be trusted or not, right? So I can talk about, again, the same slide on the same slide, right? We can see the Atlas measurements. And so what is going on there? So Atlas and CDF, again, is maybe of the order 3 sigma difference.
Yes.
So you think these measurements will improve from the Atlas side so that these error bars shrink and we can see?
I mean, you can very well imagine that we have been having conversations in various working groups with all our colleagues. I would really like it if the validation or the demonstration that you can measure the Z mass is provided by all these other experiments. So D0 has not ever done that. Atlas has not done that. Atlas has only measured it once, but they're not doing that. Now, we all have to ask the question, right? So they ask, how do you really know this thing? And how do you really know that thing? And are you making some assumption? So all fair game. Yeah. So similarly, I have a feeling in principle, the Atlas tracker is newer. It's all silicon. So it should have a similar precision, actually better precision. So one should be able to do a first principles calibration and make a demonstration like we do. But that's not there. So now if I'm asked, what kind of hypothesis can you invent which might lead to a bias in that technique, just like everybody else should think what might lead to a bias in our technique. One thought that I've always stated is a Z boson mass is an invariant mass. And that means your calibration is based on the 3 components of the momentum, right? 3 spatial components, X, Y, Z. The W only measured using the 2 transverse components, perpendicular to the beam axis, X and Y component, but the Z component is useless because the neutrino is undetermined, so there's no use of the 3rd momentum component. So in a sense, you're transferring a 3 momentum to a 2 momentum, which means you're relying on some angle to be exactly right so the 3 momentum can be converted to 2. Just trigonometry.
Hmm.
So if something happens there at the level of, we are talking of 2 parts per thousand or 3 parts per thousand. So knowing certain angles very precisely at the level of 3 parts per thousand, can we go back and look at it is what they asked me to come back and look at this or that, and I would ask them, can we come back and look at this?
Yeah.
Because there's sort of a non-closure there, right? Which may be fine, but in the end, right, we as a community are showing different ways of measuring, and you all from the outside have to sort of judge who's done it which way, who's done it which other way. We have to show you all the different ways. And the worst thing we can do is make the same mistake. Right? All 10 measurements make the same mistake. We are putting ourselves.
That would be this confirmation bias issue, right? But you're doing it in a blinded manner. So
yes.
Should be reasonable.
So many aspects of that, which also means that we do not discuss with each other while the analyses are being done.
Yeah, indeed.
So we find out details from each other after we publish. So it all has to happen in the open.
Yeah.
So keep watching. We'll be publishing more things, a study of this, a study of that.
Right. Yeah. So just another quick question. So about this ±9 that you have. So this includes both the systematic and the statistical errors, right?
Yes.
I see. And what is the error budget there? Mostly dominated by statistical, or
roughly equal. Roughly. Let me see. Statistical is 6.4 and all systematics put together is 6.9.
Okay, I see.
6.4, 6.9 roughly equal, adds up to 9.4.
In quadrature, yeah.
And 9.4 in quadrature is truncated to 9 here, which really should be 9.4.
Okay. Yeah, I see.
At this level, 1 decimal place is not good enough. So
I see. Yeah, thank you. Thanks.
We'll show it like this, which is accurate.
Thanks, Suru. Shantanu, you want to go again?
Yeah. So I guess, so the cosmology community has developed a large number of tension metrics to assess tension between various different experiments. I mean, people at IUCA are experts on it, including Surud, and your own cosmology colleagues at Duke have also written a paper on it, on applying some of these metrics. Now, I know that you cannot directly apply those metrics to your data because I think you people don't do Bayesian analysis. You people use profile likelihood. But anyhow, so those tension metrics go beyond just comparing the point estimates. They take into account the full posterior distribution.
Oh, I see.
Yeah. So my question is, I mean, how much of the data is publicly available so that some people outside the collaboration can maybe not apply exactly those same tool but similar philosophy. So I guess are the likelihoods from these experiments publicly available, and also whatever nuisance parameters you have. So anyway, so my question is how much of this data is publicly available, or is that just the people within the collaboration can do this?
That's a very good question, and in a way it's surprising, and I'm actually glad you brought it up because it could be published. My feeling is that nobody from CDF D0 in all these 5, 10, 20 years, I think you might be the first person to say this. Perhaps in your community, this has evolved somewhat recently. So somehow we never had the interaction.
I mean, Planck, LIGO, all experiments, STSS, you take any astrophysics, cosmology experiment, everything is made publicly available.
So the thing is, I don't even know what you would need to do what you're saying. That's why I can't answer.
Well, at minimum, we'll need the likelihoods. We'll need the likelihoods at minimum if you're doing a frequentist analysis. And if there are multiple nuisance parameters, then obviously we'll need the multi-dimensional likelihoods.
The quick answer is indeed there are multiple nuisance parameters. So now I'm hearing that you would need the multiple likelihoods. Okay. Very good. This is the sort of thing that happens nicely when you go to a different community, right? You're the first person who's asking.
Good, Shantanu, you should collaborate with Ashutosh.
Yes. So maybe we can talk afterwards and sort of flip through the paper. Maybe.
Right. I mean, your colleagues at Duke are much more expert on this than me. So, I mean,
maybe I should go down the
talk
hall.
to them.
Then.
Yeah.
Walk down the hall. Okay. Very good.
Excellent.
That is not with that. I mean, our community has never gone that far. I mean, in searches, in rare searches where you may have very asymmetric likelihood distributions, not Gaussian, people have probably done these things. But in precision measurements, either most of the nuisance parameters have Gaussian distributions, so it's sort of trivial. And the ones that are non-Gaussian are so non-trivial, I think people are nervous to make any statement of what the actual likelihood is. They kind of say, you will get boxed in if you make a statement like this or that, because you're mostly scratching your head for a year and trying to decide exactly how to handle the systematic. So we probably have to fool around with a couple of different likelihood shapes, maybe something long-tailed, and see what happens, right? Maybe we should get together. Okay.
Thank you. Is there any other questions? I don't see any hands being raised yet. Indulekha, please go ahead.
I'll come back to make one more comment on this likelihood business. Go ahead.
Right.
Yeah. This is a very nice question, and sorry, I'm not too sure that I understood what you explained very well. But this is regarding the calibration for the wire positions.
Yes.
Backtracking from cosmic ray tracks is what I understood. Now, is the backtracking solution unique, or can there be any offsets? This comes from a parallel sort of situation in multi-mirror telescopes, where you have multiple mirrors and they have, offsets from what their geometrically correct position should be to make the correct shape for the mirror. And then you have the mirror displacements, the rotations actually. And when you backtrack, the final shape which you get can have an offset.
Yes.
So
there is the potential for a similar thing here, and I think we have seen that in the past. I think I understand what you're saying.
Okay.
From the naive expectation, this particle has 192 measurements associated with its position. So how many dots, in other words, how many dots are you trying to connect with one single helix is 192. So a priori, it's not a handful. I can understand your situation where you have a handful of mirrors and there is a redundancy in the solutions. And if you latch onto the wrong solution, then while you're getting them to be self-consistent, they all go off in the wrong direction. So in equivalent language here, we call those strong alignment modes and weak alignment modes. The weak modes are where the internal consistency is achievable at the expense that they all get shifted up. Right? So one is up, one is down, and you try to line them up, and in the process, they all shift up or all shift down. So the internal alignment would be the strong mode, and the global position, like what you're calling the offset, sort of analogous to that, is a weak mode, which you can't pin down. So we do have weak modes. So you have to think very hard about which procedure has which weak modes, and then you have to find a different procedure where that weak mode is compensated by a strong mode. In other words, no single alignment technique, to my knowledge, has all strong modes. Every one of them has a weak mode, which I think what he is calling, you induce an offset in the process of aligning.
Okay.
I quickly flashed the cosmic ray, and then I flashed this one, where a similar technique is used, but not cosmic ray. This is electrons and positrons coming from the beam line. because these are from the W decays. And the note at the top is sort of exactly to your point, that the weak modes of one technique need to be the strong modes of a different technique so that they are orthogonal procedures. And between the procedures now, you cannot end up in some offset situation, which would actually be bad, probably for you and also for us. So we've had this question before, how do you know that all your modes are covered, that you don't have a weak mode lying somewhere that you never noticed? All I can say is that we did have weak modes in previous versions of this analysis, and they showed up in some plots that didn't show closure. So it was an indication that there is something fishy going on. So we had to come back and fix it, or figure out what it was. And so it took 3 iterations from 2004, 2009, and 2013. It took 3 iterations of improving the procedures until every check we could possibly do showed that there was no offset.
Okay.
But I can confess that all those things didn't come to us the first time or the second time. It sort of happened over a period of 15 years.
Thank you.
Thanks a lot.
Yep.
Thank you very much. So any more questions for Professor Kotwal?
I'll make one final statement on this.
Yeah, please carry on. Yes.
A lot of people within our community were always a little disappointed or suspicious that until this particular CDF measurement, which I'll quickly flash to the forward while I talk, what is often called the consistency of all the measurements made in electroweak physics, or consistency of all the W mass measurements made by so many experiments. The consistency was always a little too good. And that troubled some people. In other words, if you did the chi-square of a whole bunch of W mass measurements, you should expect a chi-square of roughly the number of measurements. Simple statistics. It was always much better than that. So there was a weird kind of worry. It's easy to say, everybody's consistent, it must be right. But some people were asking questions the other way. How can they be so consistent? I mean, you're measuring W mass for 25 years. How can they all agree with each other so well? Isn't that odd? What does that mean? So I made this particular observation about, I don't mean it in a serious way, but you just have to be careful that we all don't fall into some false complacency that because we are all consistent, somehow it must be fine. If you're too consistent, you should also be worried. So obviously when this plot got published, first reaction is, look at this difference. But some other wise old people said, maybe that's healthy. There have been such things in the past where things line up, everybody agrees, something comes along and it suddenly you get a very different answer, and then people say, we have to do this all over again, think. And sometimes things stabilize around the new measurement. Who knows the future? Because something gets realized, who knows what exactly got realized, maybe better technology, maybe better this, who knows, something new happens. And you make a step function evolves in the progress. So I'm not sure this is a step function, but in the end, we said, look, science will work itself out in the future, but the last thing we should do is somehow become nervous about it and not publish, because you never know. The whole point of science is we should just do it unbiased and publish. So from a very, very, very too good chi-square, we have now got a not so good chi-square of consistency.
Okay, great.
It's healthy for science, you never know.
Fantastic. Yeah, I mean, it looks that there are many points which are consistent with your average, but have much bigger error bars. Yeah.
And they all have a history. You know, if you go back to these lep points from E plus E minus, they've all changed over time. And so I'm now curious as to see, what decisions were made or some model was fixed. So all the lep measurements moved like this or like that. Is it the beam energy got recalibrated or some model got recalibrated? So really it looks like 4 experiments, but are they really in common somehow? That sort of thing never gets thought about until you get some wake-up call.
Great.
So maybe this is a wake-up call.
Wonderful. I don't see any other hands up, and so let's. I will thank you on behalf of everybody, but we don't have much. Thank you so much for your wonderful talk, and it's great to know that you make such precision experiments for with so many tests and come out with great results. Thank you very much, Professor.
Thank you.
Thank you.